agree this morning about what we're doing then. I just want to emphasize that the idea about Wednesday is to have a lot of discussion. We're not going to have a lot of things to present. There are some things, examples from NDN that might present if we have time, but the idea is to have a lot of discussion around the homework and your experiences running it and other things, topics of interest. So we will have more opportunities, as well as, of course, in and around the sessions that happen tomorrow. Right now, we're going to shift gears a little bit and start looking at tools and packets and moving into looking at the homework. First thing I want to do while these guys are still running is a tools thing to point out for those who haven't maybe worked with this and observed it yet. So just notice that in the current condition, what we have is that the three producers that we had from the previous exercise are all still running. They're all sitting here, they're not doing anything because the consumer finished, the consumer got the 300 and isn't expressing any more interests. But they're all sitting there waiting for interest, which means that they are all sitting there with active registrations on their faces to CCND and entries in the CCND too. And that's what I want to look at. So, you may or may not be aware that CCND can provide you some status information. And one of the ways it can provide it is in a web page. So the assigned CCNx port is 9695. You see that up there in the URL bar of this browser. And so I'm looking at the web page on localhost 9695. Now, that's a port where you can make a TCP connection to link two CCNDs together to set up a tunnel over existing IP, and CCNx communication can take place across there. But if you open a connection to that port, you open a TCP connection to the CCND at that port, and you send it a request for a web page, this is what it sends you. And what we can see is a little bit of information about the content store. Here's our 300 stored objects. There's that number showing up, because remember 300 was the number in this version of the program we're running. There's some stuff about interests and totals and things, which I'm not going to get into. There's a list of faces. So here are all these, integer numbered faces together with flags. You can look up in documentation what the various flags mean. And something about, for example, are they local faces? So here we see some local faces, which is places where the CCND is listening on IP4 and IP6 addresses and things. Here's activity rates. Well, we already know no activity is going on because none of the producers or consumers are doing anything. Here's the forwarding. This is the FIP. Okay, now there's some complicated looking, confusing stuff in here. We also probably won't get into right now, and I'm not sure if I can scroll it up far enough in here. I've got another way to look at this in a second. But down here, we see face 8, 7, and 6. And you can see that each of those faces has the prefix linemaker on it. So that's exactly what was registered based on these programs registering to receive interest. Okay, so here's an entry when in the FIP. And the face ID, if you correlate back to the faces table, will tell you something if, for example, you have a connection, you're setting up a topology and an overlay using IP and connecting CCNDs together with TCP or UDP, then you can look in the face table to see where a particular face is connected, and you can look in the forwarding table to see what prefixes are set that will be used when an interest comes along and has to be forwarded. So any interest that is in the name linemaker or something more after it, where linemaker is the prefix, could be forwarded to any of 876 because all three of them have exactly the same prefix registered currently. So in effect, this is the, think of it as a single fib entry with 3 destinations, though it's printed out on separate lines so we can show the flags and the expiry and stuff. This is a very useful tool. Another way, move the browser window aside, another way to get the same information is the command ccnd status. And that command will give you basically the same information. So this one, we can move the window up high. And you see that we get the same information about how much is in the content store, the list of the faces, current traffic values, and the forwarding table information just in text form. Yes?
I'm sorry, but what's the meaning of expired?
What's the meaning of expired? So when you have an entry in the fib, it may be that the process that registered it goes away and dies. And so you'd like to have an expired. I think that's what this one is. So it's just providing that if your process goes away, it doesn't periodically refresh this.
So you mean the application process has some heartbeat or some mechanism with the CCNd?
So it's, you say it's soft state model.
Yeah, it's a soft state model, and in fact, the Java library does have just exactly such a heartbeat. I'm less familiar with what the C library currently does in this area.
It's put in really long times.
Okay. Yeah, well, you notice that these are really, really long times. These are registrations that were done by the C library. We saw where we told the library to register, but we didn't look at the implementation of that registration. And it is setting these really ridiculously long times at present. The Java library actually does periodically, I believe, heartbeat refresh for the things that are still active. That there's still some something registered in the application for the Java library. So that's what those are about. Okay. Now, another thing that we want to do is to look at some packets, and we haven't looked at packets yet. So here, actually, let me see if I can shrink this window. Maybe I can do that a bit. X logo on the Mac. Maybe a little wobbly. Okay, so we're going to look at packets. So we'll do a wee bit of sort of general looking at packets, and then at the same time, we're going to look at packets from a particular couple of traces. And this discovery of data and versioning, we're going to address both of those in looking at these packets. Now, unfortunately, this is moving. This is a little bit of a jump from where we've been. We're moving from these very simple but stupid examples to now looking at packets that come from code shipped in the CCNx distribution. And this trace is a trace of running a CCN get file, asking for a file called park.com sample readme. Okay? Now for the moment, remember our model. The application asks for what it wants. It's the network's job to find it and to get it back to us. So let's not worry about where data is with this name. That doesn't matter at this point. Let me just assure you that when this trace was collected, there actually was data available in the network with this as a prefix. And this data was data that was stored, was actually produced, I should say, with the CCN put file program. So these are two programs. They happen to be Java programs that are in the CCNx distribution. You can run them with those command names. They appear in the bin directory and get installed if you install them. And so these are trying to deal with an abstraction of a file. Suppose you want to have a whole file. In this case, the file in question, the content of it comes from the README for the CCNx distribution. It's actually the content that's in the file system. If you look in the root of the distribution, you find a file called README. So we're now leaping to a somewhat more complicated case than we've been dealing with. But before we get into looking at some of what happens in this case and talk about discovery of data and versioning, I want to point out that this is an instance of Wireshark that is running with the CCNx plugin. So it's got a dissector for CCN. And the filter that's set here is just CCN to select that protocol. So I have filtered down to the decodes of the CCN messages in this trace. And I've selected here one packet, which is an interest packet, and here's the name of the interest packet. And if we look down in the detailed window, we can see the name is again represented. And if you expand, you can actually look at the individual components in the name broken out. And then there are other properties of the interest. That is, other fields or values that can optionally be supplied in an interest, which are represented here. And we're going to come back and talk about some of this in a moment. So that's looking at an interest. The other side of the picture, of course, is data, or a content object. And this next packet is, in fact, a content object in response to that interest. And here's the name. Now, based on something we looked at earlier today, what's one observation about this name as it's presented here? Anybody? Sorry?
Digest?
Yes. In particular, no digest. There is no digest on this name. Now, you might be fooled by looking at some of these other bits. We're going to come back to what those are in a moment as well. But if I break open the name, we see that it's got a number of components. Okay. Some of them don't print very well. Okay, so the dissector representation here is not very easy to read, or in this case, of the last component, it shows up as a blank. But there is no digest shown here. And the reason there is no digest shown here is because it's the implicit digest. And the name field in the packet does not contain the digest. And so what the Wireshark dissector is doing is it's decoding exactly what's in the packet. And so, in particular, the name field does not contain the digest here. Yes?
May I ask why this time it doesn't contain the digest?
So, where we saw the digest before was in the debug log output from CCND, which was choosing to give you the complete name, which it has to access sometimes to do the matching and things like that, like we talked about. So that was a choice that CCND made. Here in Wireshark, we're seeing a true decode of what's actually in the packet, as Wireshark always does, right? So if I select on this name, excuse me, my apologies that Wireshark also has completely hideous color choices. So in particular, you can't read any of this. But the only point I want to make about it is that down here in the bottom is the actual binary bytes of chunks of that packet. So when I select this name field, it shows me the bytes of the packet, and you can actually see, or you could see if it was readable, you can see some of the human readable letters in there. Now, of course, it selects a different part of the packet. But you can see parc.com and sample and readme and things like that actually appearing in the ASCII decode of the bytes. So the reason it doesn't show here is because it really isn't there in the packet data. Because it will be computed when required from the packet, since it's just a hash of the entire packet. So that's this idea of an implicit digest. And the implicit part is it isn't included in the name in the packet. So a content object, right, always has these three basic parts. It has the name, it has the data, and again, if you could read this with the terrible colors, you would see the CCNx reference implementation provides the libraries, because the content of this packet is part of that README file out of the distribution. That's just what the content was produced to be. So you have the name, you have the content, and you have the signature that binds them. And the signature that binds them is actually represented in two fields: the signature itself, which has just bits of the signature, and the signed info. We saw in the Python the creation of some signed info values. And what we see that's very important here is the publisher public key digest. This is the way that we identify what is the key that claims to have signed this packet. And what we see is a key fingerprint, which is partly represented there. There's also a timestamp of when it was signed, and there's a primitive content type. There's a few very primitive content types that are distinguished at the packet level, data being probably the most common of them. This just says this is a data packet. So this publisher public key digest is a claim of who signed it, and it will help us to actually find the right key to use to verify the public key signature. Now what we're missing for some reason is the key locator, and I don't know why the key locator is not working. But I don't see it here. The packet should have a key locator, which also tells you either contains the key itself, the public key, or the name of the key, so that you can go
But it's
and
not
fetch it.
every method in the Java library.
Ah, yes.
You have to find the zero object. So one of the earlier objects should have the locator.
Well, this is the first one. So,
So it might be in the
that's the inputs. This is the data. No, that's odd. I didn't look for this before, so. We'll have to ponder that one.
they're very that's
Right.
because of the Merkle tree is so expensive.
So the key locator is an optional field, and when you have a whole sequence of packets that are collectively, say, making up the same larger thing, like this README case, the key locator may not be in all of them. So how one goes immediately to show, we'll probably find one if I look somewhere. This one, one. Well, okay, we'll move on. So, there's a few, so first of all, just the basics of looking at things with Wireshark. If you have the dissector working, then you can see your interest in content objects encoded, and since those are the two messages in CCNx, that's basically what you see, what you find in the Wireshark. Now, we're going to look at some of the details of what's actually happening in this case. So remember that we ran the CCN get file program, and the name that we gave to the CCN get file program is exactly this name that appears in the first interest. So what's happening is very much like the examples we looked at earlier today, where a fairly simple bare name is expressed initially. And in this case, and this is where we start to get into discovery of data and versioning, the convention that is shared by producers and consumers related to this sort of file application is that the content is going to, of course, it's going to have to be segmented, for which we can use sequence numbers, like we were talking about earlier. So we should expect to find a part of the names we see be a sequence number part. Or we actually call it a segment number part because the problem it's solving is identifying individual segments of a much larger thing. So we should expect to find that. But in addition, and we touched on versioning before, the convention that's in use here also assumes or prescribes that there will be a version number part. So you can represent the idea of temporal evolution of this content, that there could have been something, you know, the README version of one day, and then a new version is produced by a publisher. And the simple name that the end user might be thinking of might still be README, but all of the packets have to be uniquely identified. The version of today versus the version of yesterday. All the packets are immutable. We don't actually change the bits inside the container and say, oh, it's still README and now its bits have all changed. We can't do that because all of the packets are signed and sealed with that signature when they're produced. So if we want to represent what to the user is a new version, then the way we do it is to make the version explicit in the name. So it's another thing we put in the name in our name design. So when we're talking about a name like this, and here we have a sequence number part, well, now suppose that we say, before we get to the segmentation, let's put a version. Or let's make that part of our name design. And that's the way this convention works. Now, I drew a V0 over there, and you could imagine coming up with a number of different ways of naming versions. As Van alluded to earlier, the convention that's used in library is to name versions by timestamps. And there's a particular encoding and things about and resolution for those timestamps that doesn't matter much to go into. But that's how they're named. And so when we get this initial interest and we send it out, we're expecting to find something that tells us what version is out there. And if I look at this name, so this one was our line maker name, but if you imagine this is the README, then the name in the interest went up to a certain distance, and then after that, the convention says we're going to have a version, and we're going to have a segment component, and then we have the digest. So the interest has a name, and it says, after this name, we expect at least 3 components, and we expect at most 3 components. So in order to match, the name that comes back has to actually have the right number of components after the name prefix that was specified in the interest. So that's what's going on there. And now the possibility exists that there are a whole bunch of README collections out there, different versions of different that were produced at different times. And here's a problem of discovery, because unlike the case of our very simple example where we expressed a simple interest and we get something back and we just said, okay, you know, I'll take whatever you give me and I'll read the sequence number out of that and then I'll just generate more sequence numbers from there. Here's a case where we may want to discover something about the version numbers that exist, and in particular, what CCN get file wants to do is to find the latest version number that it can of the content. And so, in order to do that, we need to use this discovery feature, which is going to involve this exclude list. So the idea of an exclude is we said, here's the name prefix. In order to satisfy the interest, the data has to have that prefix. That's the basic rule. We have this additional stipulation that it better have exactly 3 additional components after that name prefix. So we've constrained the shape of the name in that way. And what the exclude says is that certain values for the next component we don't want. We want to exclude those. So if you think about a discovery case, suppose that we had taken our initial example of the line maker program. We issued that line maker interest, and we got back a sort of arbitrary packet, but it had a sequence number. Now, suppose that in the multiple producer case, we didn't actually go over this one, but suppose that we had decided that we should have a name component that identifies the producer. So when we had those 3 producers and 1 consumer, the consumer could actually find out about all the producers and not just get an answer arbitrarily from one of them. That was the situation in that example. If you recall, one of the producers ended up getting to supply the data, and I think we didn't say explicitly at the end of that was that which producer got to supply the data was essentially arbitrary. It was a matter of timing of which producer happened to get the interest first and be able to answer with a content object and get that back to the consumer first so that their sequence number got picked. That was essentially arbitrary. Suppose instead that we had wanted the consumer to be able to find out about all of the producers that were out there and pick one of them on some criteria of its own choosing, or maybe actually retrieve the data from all of them. Then if the producers just had a name, and the name might be something like the hash of a key or some name that they made up, there's no simple logical like integer sequence to those names. We have to discover what the names are that are out there. And the way that we can do that discovery is to use exclusion. So imagine we emit our first interest, and we get back one object, and it's arbitrary, just like in our example. One object comes back from one producer, and we can look at the name that came back and we said, now I know the name of one producer. I don't know the name of any other producer. If I want to get all the data from this producer, I just extend my interest to include that producer's name component, and then I'll be able to pull data from that producer. But if I want to know about other producers, I say to myself, well, now I know the name of one, but I don't know what the other ones are, and I can't compute from the one I have what the name of anybody else is. This is what's different from the sequence number case. In the sequence number case, when I got a starting sequence number, the convention was the next sequence number is that one plus one. So I could entirely independently compute what the next sequence number ought to be. But if I'm dealing with these producer names, I can't do that. And if I'm dealing with version numbers, I can also have some of this problem because I don't know when the versions were produced. I have to discover what versions are out there. In the version timestamp case, I might be, as here, looking for the latest version, so I have an additional constraint. But basically, I have to do some discovery. So imagine that I get this packet back with the producer name. Okay, now I know that one. So what I'd like to do is modify my question. I'd like to ask the same question in the same name, but I'd like to tell the network this time, I already know about this one. So if you find a match that has this piece as the next component after the name I gave you, don't send it back to me. I already have it. I don't need that one. So we do that with an exclude specification. So we can put in the exclude specification something that says, here's a name component I already know about. I don't want anything that has that name in it. And this is allowing the consumer who knows what he knows and knows what data it needs to be more specific about what it's requesting from the network. And this is an answer to the how do you do low-level discovery question that was asked earlier. And you can do it in this mechanism, but without an ability to do excludes, you've got a problem. And that's why this bit of machinery in this field is here in the inputs. So in this case, we've lucked ahead to an example involving versioning. So our convention says, like over there on the board, that after the base name, the next component's going to be a version stamp. And what we do is we use a convention for how version stamps are encoded and formatted. And that convention involves a special prefix, which is this FD value, and then a binary encoded timestamp value. And so what we're doing here is to say, and this is a little tricky, this exclude in this packet essentially says that we want to, the star means exclude everything that is lower in the calling order than this value. And the star on the other end says exclude everything that's higher, that's greater in the ordering of components. And there's a defined total order on component name, component values that makes this work. And then it says, let's basically be within this range of values in that total order. Now, this is the bare name. At this point, the program doesn't even know any single version number that's out there. All it knows is it wants this base name and it wants a version number. And what this exclusion here is doing is it's trying to rule out the possibility that somebody made some data that said readme and then Tom or something else that's not even a version number. So we want to at least limit ourselves to the space of version numbers as they are encoded in this convention. And that's what this exclude is basically accomplishing. And then we see this child selector field. Now, suppose that this interest goes off to and reaches some content store in some CCND. And suppose that that content store has a whole lot of packets with this prefix. And every one of those, and let's say it's got them, and they actually have several different versions. So if they have versions, they all match the pattern for versions, so the exclusion is going to allow them. But we talked earlier today about the fact that one interest yields one data. And that means only one data can come back. Now, the CCND gets this interest, and it's got a whole bunch of matching content objects, let's suppose. Which one does it send back? That's what this child selector is about. This child selector value is decoded here to say rightmost greatest, says if you've got a whole lot to choose from that all have the same prefix, then pick one where the value in the next component is the greatest you've got. And when we're trying to discover what is the highest version available, that's a pretty useful thing. Notice that CCND can implement it entirely based on the total ordering of component values. So CCND doesn't know anything about versions. It doesn't know that you're interpreting this value as a version. It doesn't care. All it knows is there's a total order, and it's been asked in that total order to give you something that is the greatest value it's got in that next component. And as long as you design your name convention, this comes back to the name design problem, if you design your name convention so that greater versions sort later in this total order, then you can use this machinery to get the highest thing that a particular CCND has. And that's what's going on here. So that makes our initial interest. I should mention that this FD thing is an example of a convention pattern we call markers. And there's a, in one of our protocol specification pages here, we have basic name conventions. And this page describes, I'm looking for versions, marker FD, it explains why sort of markers are designed the way they are, and tells you about the specific ones that the current implementation supports. So you can look there to see a marker, and where my cursor went, here, sure enough, there's some evidence that we're using in the case of that marker. That allows you to have some assurance that the producer actually intended this to be a version. It's just a convention, and somebody could choose to ignore it and use that name organization for something else, but it's a convention that's used a lot in the library. And that's our interest. Here's our content objects. Content object comes back, what do we get? We get a name, it's got the prefix of course, and now it's got an FD with a specific value, 04F6M40CD91. Got a specific value. Oh, and it's got another part. And that other part is an encoding of the value 0. And that is according to the segmentation convention that's implemented in the library. So that says this is segment 0. So we can, and this is just sequence numbering like we saw before. So we know that the next packet of this version of this README content is going to be segment number 1. So now we've got our hands on a specific version. This is very much like our sequence number discovery. We asked the first question, we got back an answer, and that answer told us something we didn't know. It told us one version name that exists out there in the network. We turn around next, and we issue another interest. And this interest, you see, is an interest in exactly the same prefix name, but this interest has a different exclude. Now we exclude everything from the version value that we got. We already know about that one. Don't want to hear that one again. And we're still asking for rightmost greatest. So we're asking the network to tell us about some other name, the data for some other name that's beyond this and is still the greatest one we've got. Because our interest might have been answered by one CCND that gave us the greatest it had, but it might not be the greatest that's out there in some other CCND. So this is what the library is doing. There are other ways to address the problem of finding the latest and not having stale copies lying around in the network. Content objects can actually have a stale time set on them so that the CCND will age them out of its cache. And that can allow you to limit the frequency with which interests have to go all the way back to a producer, and yet allow what's in the network to be basically current. And we don't, unfortunately, have a lot of time to talk about staleness. It comes up, I believe, in one of the homework exercises. So you should know that staleness is something that a producer can set inside its content object in the signed info, and that is something that one of the homework exercises will look at. So
it's probably worth pointing out that not setting the default staleness we realize is a design mistake.
yes, thank you. Right. So what Van's alluding to is that the implementation of libraries that we started out with and have had basically up to this point did not set a default staleness. So by default, content just hung around forever. And we realize that's a design mistake, that typically content should have some staleness. And so we're going to be making changes to the library so there is default staleness. But it's,
and that makes this go very much easier. If your data is going to go stale, if any version that you've got is going to go stale, say after 4 seconds, then you don't have to express interest. Discover a version, express an interest in the next version so that you get to see what's beyond the version that's sitting in the caches. You think if you don't have staleness, you have to sort of go through CCND by CCND, discovering old copies and excluding them so that you find the next one. And that's all happening because the data sits around forever. Another important design thing in this information-centric architecture is you need to make data go away. Like all those bugs from not restarting CCND, well, as Jim pointed out, you can't restart CCNDs all over the world. Your data is going to be hanging around. It's sort of like my daughter learning that the stuff she posts posts on Facebook, never goes away, it hangs around forever. And even though 6 months later she's embarrassed by it, she would like it to go away, you can't make it go away. The distributed environment data is persistent. So you've got to architect, engineer your data going away to make lots of problems easier. And that's the point of this staleness, which unfortunately we realized that the hard issue was not making data, it was removing data, it was making it go away. Producing is easy. We realized that sort of too late to get the defaults right in the library, and so we're going to fix that at the next revision. It's another thing that's showing up in 0.6.
Okay, so that's why this other interest, which is gone. That's why this other interest was generated in the same name prefix. Is it's trying to probe for additional versions. Now, it happens. I'm just going to tell you that there aren't any additional versions in the world in which this trace was captured. But that's why it's doing it. The next thing that we see the program do is to emit an interest for something called .header under this funny prefix under the version stamp. And this is because we've got another convention which is sort of odd and in a funny state. It's not being used very much, of a notion of metadata about a whole stream of content objects. And these programs support that, so that's why they're asking for it. But we're mostly going to ignore that at the moment. And unfortunately, for historical reasons, they asked for it under two different names. So this is the second ask for it under the underscore meta underscore name. And the previous one was using a marker convention, which is what we use now. Now, here we go. Here is our interest for the next segment of the content that we actually want under the version we found. That other version interest to try to discover new versions, that interest didn't come back with anything new, with any new version. So the program is going to press ahead with the version it knows about, which is this one ending with CD91. And now it asks for the next sequence number. And you see that this %00, %01, that's a trick of the encoding. This is how the sequence number value 1 is encoded. And these are using the percent notations in the URI encoding because these are actually binary values, very compact binary values in the name component. So to print them out, they have to be shown in this way. And that's just the way we happen to be encoding those numbers. Ah, yes, thank you. And then min suffix components and max suffix components, that has gone down to 1. Why is that 1? Can anybody tell me, guess, why that's 1 at this point? It was 3 when we issued the interest in the bare README name, and now it's 1. We've already got 2 more, the version and the sequence or segment number components. So we want something which has exactly 1 more. That 1 more is the implicit digest, which doesn't show up in the packet we code. But it is formally part of the name and it's part of the matching, and so it counts for the min and max suffix components.
I think it's for so in this namespace, it's not like the file system. Every name can both have data associated with it, and it can have additional name components. It's like every file could be both a directory and a file. It can have content, but it can have other names associated with it, like that metadata pattern that Jim showed before. So what's being said here is this name names a data object. The only answer that's acceptable here is actual data, because actual data is the only thing that's got 1 additional suffix component. That's the implicit digest, which is the digest of the actual data of the file. So it's saying, even if there's a lot of other junk laying around, metadata describing this object, author identity, you could have lots of other things in this namespace. The only thing that you will accept here is a block of a file, something that's got data associated with it. this is the name pattern you see when you get down to the complete name for a chunk of data.
Okay, so we had an interest in one chunk of data, the segment 1 chunk of data. Now remember, we had this interest in a header outstanding before, and we've actually got an answer for that. But I'm going to skip that because we don't have time to go into the whole header mess. Now here's a content object. And this content object has the name that we exactly want. Here's our version stamp, the CD91, and here's our 0001, which is the encoding of segment 1. So this is the answer to that interest we looked at a moment ago. And now we get an interest in 02. And now we get an interest in 03. And now we get an interest in 04. And now we get an interest in 05. And then we get a content object, which is 02. So what do you make of this run of interests? There weren't any content objects there. Why am I issuing more interests?
Improve performance.
Yes, to improve performance is the answer. If I issue an interest only when I get a content object back, then I have a stop and wait protocol. And so this is pipelining. Although one interest will fetch at most one data, there is no reason why you cannot issue multiple interests in parallel as long as you can predict what the names will be. And here we have a convention that exactly allows us to do that. We know that the names of the packets we're going to want next to retrieve all of this README of version CD91 are going to be named 1, 2, 3, 4, 5, and so on. So we can issue some number of interests ahead. And those interests, by the way, may get reordered. The CCND may forward them in a different order than they came in. And so we may get data back out of order. But that's perfectly fine. We can do sort of, if we're providing all of this as a stream to some application above us, we can do reassembly over some window that we allow of how many interests we'll get ahead. And that's exactly what's happening here. So this pipelining is present in the Java library stream abstraction implementations. And there's also some examples of it in some of the C programs that do reading, where multiple interests get issued, and then we get the data back and fill holes. So we finally get there's our interest for 5. We finally get the content for 2. We get the content for 3. And here's our interest for 6. Now, we're going to look at something special about the content for 3. In the signed info for the content for 3, we have this additional field we haven't seen before, and it's called final block ID. And this is a special annotation to tell the consumer that the producer who signed all of this, including this annotation, says that the last object of content in this series has the name component 3 as its sequence or segment number component. If you get, and the convention here is if you get a content object that says its final block ID is 3, and it is in the content object name 3, then you know you're done. If you get in, say, content object number 1, you get a final block ID that says 3, which didn't happen here, so I can't show it to you in this trace because it wasn't put in. But if that happens, then the final block ID in that case should be treated as a hint, because something may change while the producer is producing this content. So you don't necessarily rely on it, but it's a hint maybe you're not going to get past 3. But when you get to a block that's called 3 and it says the end is 3, that is the way that the producer says, this is it. This is all I produced. And because this is all covered by the signature, it can't be faked by somebody who gets the packet in transit and modifies it. So this is a reliable indication from the producer It's not the only way you could do this. You could have a separate metadata content like that header that I talked about, and it could say how many blocks there are. In fact, it does say how many blocks there are, but the library doesn't really use that information. It does tend to use this. So what we see at the end of this sequence is we see that we got the content object 3, which is the last one. This README file is not that huge, so it doesn't split into that many packets. And then we still see an interest coming out. Okay, so there was still an interest coming along from the pipelining way out at 6, because there wasn't even a hint. So the program doesn't actually know when it's going to have to stop. It's issuing interest out ahead of where it is. And the reason there's nothing more in this trace is because after this interest went out, it had processed the previous content object, at which point it knew that that was the end, and that's where the pipeline got killed. And so no additional interests were sent out. And the interests that were sent out previously for 4, 5, and 6, and 4 and 5, and then subsequently 6, they never get answered. There is no data for them. And that's just fine. And once the application has processed this, it knows that there's no data for them.
The entity that controls the pipelining is application layer.
The entity that controls the pipelining is application layer.
So each application should consider the magnitude of pipelining.
Yes, so there's a question about what is the right magnitude of pipelining. This is implemented in the library, say in Java. This is a Java program. It's using the Java stream abstractions. And the library actually implements the pipelining, but has an adjustment. You can adjust what the pipeline size is. This gets into a long other discussion of how we manage the balance of how many interests can be outstanding. And the current implementation doesn't have any help with that at all, nor does it deal with timing and re-expression, sort of what interval you have to maintain that soft state in the pits at. So this is all work yet to be done, because what currently happens isn't right. Currently there's a fixed 4-second re-expression timeout in the library code that does automatic re-expression, and that's not the right thing. And you can send as many interests as you like, and the CCND will just try to cope with them, and has no feedback mechanism to tell you, no, I can only deal with 14 interests from you. So you could crank the pipeline up to 150, and it wouldn't actually help you, but you could try it. And the CCND doesn't protect itself very well against such things. So those are all areas of additional work that we don't have a lot of time to talk about right now today. We might get into talking about them later in the workshop. So this is the basics of putting together some of the things that we looked at earlier today in the examples into a more complex, complete scenario where we want to retrieve a whole set of content that sort of belong logically to one version of the file. And this is how you can look at the packets and see what's going on. Now we didn't yet look at the code for this, but the code for CCNget file, which I will very briefly show, involves getting a handle. We're going to actually write the file to someplace, so this is normal Java file system stuff in here. And then, depending on some flags, because this program does a bunch of different cases, the case that we were in is using this CCN file input stream. So we give it a name, which in this case was an argument supplied to the program by the user. And that was that name, CCNx.park.com example readme. And we have the handle. And then in the Java library, we called that input, and we're able to simply read it like other Java I/O streams. And so at the level of the program, this program is treating it almost like it was a file, because the library is worrying about issuing all of those interests and figuring out what the latest version is and getting you all of the segments, and then just supplying to the application the bytes into buffers that come out. So this is an example of a high-level abstraction that is implemented in the Java library. There is also some string support in the C library. It works very differently, but it's the same basic idea, sort of create a stream and be able to get data out of it, so that the library is taking care of dealing with all of these conventions, the kinds of things that we talked about that tend to show up near the end of names, where many applications have a need for version, many applications have a need for segmentation, so the library can just implement the same convention on behalf of all these applications. So that's what's going on there. There's one last case to show, and then we're going to start switching gears to the homework and running some things. So I need to just change files here. There is something in the homework which also deals with a repository. It's the function version exercises, and the CCN put file program is a program that stores things in a repository, and this comes back to something else we talked about earlier today, which is the use of an interest to trigger some behavior. So the way that I put something in a repository is the repository is listening for interest in the content namespace it deals with, which it has to do in order to supply content when somebody asks for it. But we have special marker conventions. We can construct interest in a special way that tells the repo that someone has new content that the repo should fetch itself. So now the repo's role reverses. Instead of being a supplier of content when somebody else asks with an interest, the repository turns around and starts issuing its own interests to fetch this content that it found out was out there. And every time it fetches one of those packets of content, it stores it away in its stable storage on disk and keeps it indexed so it can supply it back to somebody later. Here we have an example of running that CCN put file program. We'll fix the colors there. And there's some other stuff at the beginning that I'm not going to go into, related to getting keys for things and the repo and stuff like that. But here's a case we're going to look at. Here's an interest, and here's the name in this interest. Now, this is actually saving the README file that we retrieved with the other program, the other trace. So it's got the same prefix of the README, and it's got the version stamp. Now, in this case, this is the producer, right, of the data. So the producer has actually picked a version timestamp. It didn't have to find it out, it's the producer, so it picked the timestamp. In this case, it would probably be the timestamp at which it was making this content, or else the timestamp on the file it came from, one of those two. And now look at this %C1 RSW. That's using another one of our marker conventions, and the SW stands for start right. So this is what we call a start right interest. And in this interest, there's an instruction to the repository to say that it should start pulling data whose name has the prefix up to where the start right appeared in the name. So that means all of this with the README and the version stamp. What follows, the last component here, is using another one of our conventions, %C1.n, and then a bunch of binary stuff. And this marks a nonce. That's a random number that's used in this case to make sure that with high probability, there is not already data out there answering the start right. So it's bypassing anything in the cache and making sure that this interest gets all the way to the repository. When it gets to the repository is going to look at this interest. It's going to look for this special marker component and say, aha, this is not someone asking me for content. This is somebody telling me about some new content that's available now on the network that I should fetch. And it will strip off everything from that component on. We'll strip that off the name. And it will turn around and start issuing interests in the prefix to pull that content. And first of all, before that happens, we have to observe that just like any other interest, this interest gets a data back. And so, of course, it has the same name. And What this content contains, though we won't go into it, is it contains a bit of information about the repository that's answering, basically. And it's a kind of confirmation that some repository out there is really going to listen and wants to start pulling the content. And here's an interest from the repository asking for segment 0. The way that this start write convention for the repository works is that it assumes that we're dealing with segmented data according to the segment convention we just looked at. So that means that it doesn't worry about trying to find a version or anything. It was already told that in the start write interest. So it basically goes right ahead and starts asking for segments. And it will ask for a number of segments. Now here it got the first one, the 0 segment. There it asks for the 2 segment. And it gets the 2 segment. Here it asks for the 3, and it gets the 3. Here it asks for the 1. So here's an example where some reordering happened in the pipelining that's going on. But eventually we do get 1. And so, or sorry, we do get the interest for 1 out, and then we get the content for 1 back. Yes, question.
Actually, this repository is still a very mysterious for me. Maybe because it wasn't in the paper. Actually, when I heard about this repository, I thought that it's a kind of database for only for the data producers. So now what you say is it's like a cache, or it's going a smart cache is going to find data on the internet and put download. So you mean all the routers in the network they are going to have a repository and then put another traffic on the network?
No. So routers don't have to have a repository. There's no reason that that's required. Here we're looking at a case where the repository is actually on a local node, and you get it as a stable store of content that you can retrieve later. But the repository also is, it's not going off to find data like a cache where it has a miss. If it gets an interest and the data is there, it will supply it. If it doesn't, it won't. And all we're showing here is a protocol for explicitly telling that cache that it should put something, or that repository that it should store something.
So I might go back to the start write interest, because you didn't point out the scope.
I did not point out the scope, that's right. So we need to go back and do that. And here it is. So, so something I didn't point out when we made our first pass over this is that there's another field in the interest that we've never seen before. This is the scope field, and this limits the propagation of this interest. There's a number of scope values defined. You can find that in the protocol specification for the interest message. This particular scope means when a CCND gets it off of a face, it can forward it to any other local face, but it can't forward it to any face that is non-local, which means it doesn't leave the machine. So in fact, we're asking here a local repository to hold on to this content. And in fact, the scopes are defined this way because there are a few boundaries that are actually significant. This one, which is doesn't leave the local machine, and there's another which is will go 1 hop, will reach my neighbors, which is important for certain kinds of routing discovery and things like that. So there's, and then there is actually one that's defined for only answer from the content store and don't send it to any other faces and things like that. So there's a very small number of scopes that you can use. And yes?
So you have 2 versions of CCNx, one for routers and one for client?
No. So the thing here about repository, this repository is really focused on being a local store of content to help a node operate, the kinds of things that are the persistent state, so when your node reboots and everything, your apps have it available locally and they can ask for stuff to be written. And by default, whenever you use the APIs and the commands and things to write to a repository, they do scope 1 unless you take special measures to support that kind of idea. The kind of thing I think that you're getting to is the comment I made earlier today about the fact that you might think of a router, of a repository as being analogous to like a storage blade in a router. So that is an optional component. And in that configuration, if you were to have such a thing in a router, it might be operating as a cache. And so its operation would be different than this. It wouldn't necessarily be told explicitly to hold stuff. It might be holding on to everything that comes by, you know, according to its replacement policies and things like that. So those are other scenarios that involve persistent hanging on to data, but it's not quite the same as this one.
An issue that we discovered a couple of years into the project is you go beyond pure broadcast fiber propagation. The network needs information about its own functioning. So things like routing cables, they have to live somewhere. We would like to use this model because it gives you broadcast data, very scalable broadcast data, multiple senders, multiple consumers, which is something that things like routing rely on because they require distributed agreement. All the data is signed, so you get strong notions of provenance. It's much harder to attack than BGP or OSPF. So it's a nice transport information for network, transport mechanism for network internal information. But you would like that information to be stable. You don't want to lay it into a transient cache, which is what you've got in CCNd, right? That's really buffer memory. It's just to absorb bursts of traffic and to handle minor timing variations. When you get routing prefixes, when you get keys that authenticate other routers, you'd really like them to hang around because your operation depends on it. It seemed really important to have an architectural element that you could count on that was the storage abstraction. And that's why the repo is increasing its role. And we're going to talk some on Wednesday about, once we put that in, we realized there was a completely different model of transport possible that was way more efficient and more scalable than what we've been using, that integrated the storage and communication kind of better way. So, saying the maturity of the project made it more obvious that we needed this repo, and this seems like a good model because you have very fine-grained control of exactly what goes into it, but it fits really seamlessly into the CCN model. Whatever you tell it should be inside, it automatically supplies to anybody who's going to ask. So it doesn't require any sort of configuration or any sort of setup. And some neat things can happen once you have it there.
Great. Great question. Thank you. So now we're going to have to switch gears again a bit as we move towards the final.
So one thing before we go on, why don't you put up the interest description from the documentation?
So this is in the protocol specifications part of the documentation, and it's the CCNx interest message. And here are all the parts. So we have seen name, which is the sole required part, no question mark on that one. We've talked about nin suffix and max suffix components. We have not, there was a side conversation about publisher public key digest. This is a way to say that the content object you want back must claim to be signed by a particular signer, particular fingerprint, key fingerprint. We've talked about exclude. We've talked about child selector. This is the thing that says, you know, give me the latest in the ordering sequence, or alternatively, you could say give me the earliest in the ordering sequence, which you might do if, for example, you had a segmentation number convention, but you didn't know where it started. Instead of it always starting at 0, like our current convention, maybe you wanted to find the earliest thing. And so you could set the child selector to say give me the earliest. Scope, we talked about scope. I'm skipping answer version 9 in a minute. Interest lifetime is not fully implemented yet, but is part of this whole issue of how we deal with the lifetime and refresh and things of interest, and balancing the amount of re-expressing, resending interests with the lifetime things. And we have not talked about nonce yet. So which do you think are most important to touch on, because we don't have much time?
Actually, I didn't want to touch on. So last time we tried to teach this class, we sort of started with this page and went through that list. But when you're learning protocols, right, you're learning about Vint Cerf and Dave Clark's work, stuff that they did in the 70s, and by the time you see it, it's got 20 years of history, and sort of they figured out all the answers, and it's just presented to you as this is the answer, this is the way that you do things, but you don't know why it's the answer, and you don't know what any of the options were. And every time that you present a list like this, you tend to look at it as, okay, that's the answer, I'll memorize it, so what? But all of the things in TCP/IP and all of the things in NDN are there because they solve some problem. And we didn't get God to write down on a stone tablet, this is the way an interest should look. We tried something and it didn't work. And then we said, okay, well, how the heck do we fix that? And so you try putting in a name that's not engineered right, and you get things out of a cache. You say, okay, I need more components. You then try to have multiple servers, and you can't discover them. You try to have multiple versions, and you can't find the most recent one. And each of those problems, first you try to solve it with the mechanism that you've got, and if that doesn't work, you try and figure the minimum mechanism that you can put in that solves the problem. So what we were trying to do today in this class was to take you sort of along the road that we followed, but for us it took years, and we tried to go through it in a day, which is show a simple example of a problem that we had run into, and then show the mechanism that was used to solve that problem. So you get an idea of why these choices were made. But this is very much a work in progress, because there are things that are here that we know are wrong. There are things that are missing. We don't know if this will solve all problems. We'd like it to be simpler than this. But the way that you get a protocol architecture is you try things, you have an idea of the direction that you're going, you try things, you find places where it doesn't work, then you try to find a mechanism that will fill that hole, and you make it parsimonious, the minimal mechanism that will fill the hole. So that's why we took you on the trip through these different pieces, which all came in response to some particular problem. And we've taken you through pretty much every one except nonce, which is tied into topology, which we'll try to get to. It's not needed for the homework, and we'll try to get to it on Wednesday.
Yes, great. And likewise, think about a couple of the things we just mentioned in the last hour or something, the recognition of the repository as an important component for how many nodes to have. The recognition that we should be setting stale times as defaults on a lot of the content that's published, right? These are all things that have changed, or our understanding has changed. And likewise, there can be things that actually affect what's in the protocol. Okay, we're trying to get through the list. I see that there's a question starting. Is it a quick one?
About this protocol, I think some other internet architecture they also introduce the caching in the network, but normally they use exact match. But in NDN, I think in the interest they give some policy to define which caching they want. My question is, in distributed network, each network node has different pattern for that. that means if you send same interest, but different nodes may respond different to that.
So, see, there were two things in what you said. The problem with using exact match is, what that means is you're going to route your network flat. And we know that doesn't scale. Okay? Nobody's been able to. There are statements that you could make a 1,000,000 node distributed hash table, and that would allow you to make something that's almost the size of the internet. And it's technically possible to make such a DHT. Who would run it? Is your government going to run it? Is Google going to run it? Microsoft? Do you want to depend on an internet where some single entity, because a DHT, since it's flat, it has to have single administrative entity. You can't partition it. And so there are lots of economic and social consequences of making that decision that, as you go down that architectural road, it starts to make less and less sense. So if you've got structured names and you're doing longest match lookup, then you can easily encompass flat. If we want to put in DONA names, just say DONA/long cryptographic identifier. Because in longest match lookup, it's the contents of the routing table that describe the structure of the names, not the names. And so you can embody flat names in this architecture, but the opposite isn't true. You can't embody structured names in a flat architecture. So this gives you the most options, and it's known that longest match and structured names scale to the size of the internet because that's what the internet uses. That's what our content, that's what the web uses, that's what our addresses use. It's the single scaling mechanism that's been used across all the different ways that we put data into the internet, both conversational data and content data that's sitting in the webs. So this has got a pretty good track record, and the experiments with flat have been pretty disappointing. It has some serious scaling and operational issues.
And with that, we have to defer more discussion of that topic. It's a great topic, but I'm looking at the clock and we have to keep moving along. So what we need to do now is I need to shuffle some things around, and we need to have a little huddle about how we're going to do the next part. So what we're going to do is it'll probably take us at least 5 minutes or so to do some of this, but I have something for you to do while that's happening. So what I want to ask, I see many of you have laptops and machines open in front of you, maybe not quite everyone. If you have something available that you can get on the web and use the Wi-Fi information, go to the website for this event and find the homework description if you have not already done so, and pull up that homework description and start to read over it, sort of take a look at it, familiarize yourself with it a bit, so that we can try to catch some immediate questions that may come up about it. And we're going to shuffle some stuff around and huddle and give you a little more information about how to use a resource that's being provided to help you actually communicate with one another between your programs when doing the homework. So take a look at that, think about things, take a break from the game, but this won't be very long.
컨텐츠 퍼블리시하면 자기 노크를 리포지터리 들어가서
근데 어떻게 들어와요? 애가 차여서 거기다가 메인으로 돌리면 개인 보관하면 나 개인 보관하고 있어. 아, 그 차이 없지. 개인 보관하면
아 그렇게 할 수도 있겠네.